So in our last lecture, we had done some binary arithmetic. We had covered all the four operations, the operation of addition, multiplication, division, and subtraction. And in today's lecture, we will review some of the Boolean algebra that you have already done while you were either in school or in junior college. So we will review in Boolean logic. So we have Boolean logic, and in this we have, if you take any variable, a variable can have only two possible values. So Boolean variable it can just have and these values are 0 and 1. Okay. Sometimes we may call this as false, this as true. No, yes. So it depends how you denote it. Okay. So there are different ways in which it can be represented, but we will be dealing with 0 and 1. Either a 0 or a 1. Now, in this particular lecture, we will review some of the things which we already know about Boolean algebra, which is required very commonly in mechatronic devices. When you are having a mechatronic device, you would like to program that device or make it behave according to a particular logic. If this condition is fulfilled, this condition is fulfilled, this condition is not fulfilled, then this should be the output. So what you are doing essentially is dealing with Boolean logic. And that's where you're dealing with Boolean algebra. So we need Boolean algebra because we would like to formulate the logic and then simplify the logic so that our logic becomes economical enough for implementation. So Boolean algebra is what we will be reviewing. Now in this, a Boolean variable, let's say a Boolean variable A. This Boolean variable can take two possible values, 0 and 1. Now, you have certain fundamental operations which are possible on this Boolean variable. So, let us look at some of these. You must be familiar with this. You have a NOT operation. If you take the complement of A, we also call it NOT of A. So this is not A. And it's denoted like this, A complement. So A with a bar on it. So if the input is 0, your output will be 1. If the input is 1, the output will be 0. It is just going to complement A. And you can denote this in a particular manner. You can represent it graphically also as a NOT gate. So you can represent this as a NOT gate, symbol for which is like this. So if you are passing on the variable A as the input, you have complement of A as the output. Okay. Now we can do a number of other things, but we need some more operators. We also have the AND operator, and I'm sure you are familiar with the AND operator. So you have the AND operator. You also have the OR operator. So these are operators. So you have the NOT, AND, OR. These are operators. You can perform operations with these. So they operate on Boolean variables and they produce certain results. So now suppose we consider, we have already considered the NOT operator here. So A and NOT of A. So we made use of the NOT operation. Let's look at the OR operation. So for OR operation, if we have A, so we can take A uh, and we can OR it with B. B is another Boolean variable. So you can have certain possible values. You can have A as 0, B as 0, A as 0, B as 1, A as 1, B as 0, and A as 1 and B as 1. These are possible input combinations to the OR gate or to the OR logic. We can also write this, instead of writing it as OR, we can use the plus sign here. So A or B. So we can use a plus sign, and this plus sign denotes the OR operation. Now let's make some lines. So here we can represent 0 or 0. So 0 or 0. And you know the answer to this is 1. 0 or 0 is 0. Okay. 0 or 1. The answer to this is 1. 1 or 0 is 1. 1 or 1 is also 1. So this is the result of the operation A or B. We can represent the OR gate using a symbol like this. You must have already studied it in your basic digital devices. Oh, I'm sorry, it's not the OR. It's the so can have the inputs A and B, and A and B can have these possible values, and this is the output A or. So this is a representation of the OR gate. Now we also have the AND gate. So we may have operations A and represented by this operator and B. So here we may again have these possible values 0 and 0, and the result will be 0, 0 and 1. The result is 1, 1 and sorry, 0 and sorry, this will also be 0, because when it is 0 and 1, it is 0, 1 and 0 is also 0, and 1 and 1 is equal to 1. Now the AND gate, the AND logic can be represented graphically using the AND gate. So again, you have the two inputs, you have A and B, and the output is A and B. So the logic is like this, that if both the inputs, any one of them or both of them are 0, then you get output as 0. So only when all are ones, you get the output as 1. You can also proceed further with the the complement of A or B, which we call as NOR logic, NOR gate, represented by a NOR gate. And here you already have A or B computed here. So you just have to take the complement of this. So here you had 0, so here it will be 1. Here you had 1, so here it will be 0. 0, 0. It's just a complement. And in order to represent the in order to represent this gate, we can write it, we can represent it like this. So you have the inputs A, A or B and complement of that. So this is actually A NOR gate. So this is A NOR A. This is A and B. In the same way, you can have a NAND gate, A and B, and complement of that. So here you have A NAND. So here you already have the output of the AND operation here. So 0, complement of that is 1, 1, 1, and here you have 1. So complement of that is 0. So you have got the NAND gate, and the symbol for the NAND gate is just like your similar lines, except that you have. So you have the inputs A and B, and you have A and so these are the fundamental operations. You have an exclusive OR, exclusive NOR, exclusive, and you can make a combination of these. In an exclusive OR operation, uh, so you will have whenever all the inputs are 0, you will have 0, and when all the inputs are ones, also you will have a 0, and in between all the others, you will have 1. So that is the exclusive OR logic. Now let us come to certain basic fundamental laws that we come across. I will make use of some of these, of this line here. We'll save whatever we have done so far. Next slide. So now we are going to review some Boolean laws and identities. You already know this, but we are just reviewing it because we will need this as we use review of Boolean laws and identities. So let's come to the fundamental laws. And in the fundamental laws, we have, let's do them for the OR gate. So you will have, or let's start with the NOT. Okay. So if you take the variable, Boolean variable A, and perform a NOT operation on it, you get the NOT of A. Okay. And this will just complement whatever value you have. And if you further complement it, you will have NOT of A, which is equal to A itself. So this is when you are inverting A twice. We can also try for the OR logic. So this was for the NOT logic. If we try it for the OR logic, um, we can start with A or 0. Now, if you see A or 0, take various combinations of A, you will get, if you take A as equal to 0, or it with 0, you get a 0. If you take A as 1 and or it with 0, you get a 1. Can you all hear me? Hello?
Yes.
Yes,
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 sir.
sir.
Yeah,
Yes.
I'm continuing. If we, uh, so you can see that if we take A or 0, if A 0, it is A or 0 odd with 0 is 0, 1 odd with 0 is 1, and so you always get the same thing as A itself. So you can conclude from this that A or 0 is A itself. Okay. So this is one Boolean fundamental identity. We will keep this in a box. Likewise, you can take other. You can take A or it with 1, and if you take value of A as 0, you or it with 1, the output is 1. Take A as 1, output or it with 1, also the output is 1. So A or 1 is always equal to 1. Okay. So this is another Boolean identity. You can keep it. So this is similarly, you can take another Boolean identity. You may consider A or A. It's not two-way. This is not your normal algebra. This is Boolean algebra. So here, what is it going to be? If you take A as 0 or it with 0, the result is going to be 0. If you take A as 1, you or it with 1, the result is 1. So A or A is going to be the same as A itself. Okay. So this is another identity which we have. We'll take one more identity, and that is A or complement of A. So this is going to be equal to what? So if A is 0, and or it with complement of A is 1, so the result here will be equal to 1. If A is 1, complement of A will be 0 and the result will be 1. So A or A complement is going to give you the result as equal to 1. So this is another identity. Here, so these are four identities that we have got related to. These are related to the OR operation with A. Let us see identities related to the AND operation. So let's take A and 0. So if A is 0, you AND it with 0, the output is 0. If A is 1, AND it with 0, the output is also 0. So you can see that if you AND A with 0, the output is going to be 0. This is another identity. Likewise, uh, so we can take A and 1. So if you take A as 0, AND it with 1, so this is going to be equal to 0. If you take A as 1, AND it with 1, you will get it as equal to 1. So you can see that A and 1 is always going to be equal to A. So this is another identity. We can also see A and A. So if you take A as 0, ANDed with 0, the result is 0. If you take A as 1, ANDed with 1, so the result will be 1. So you can see that A and A is A itself. It's not A square, A itself. This is Boolean operation. And if you take A and complement of A, taking A as 0, ANDing it with 1 will be equal to 0. Taking A as 1, ANDing it with 0 will be also 0. So when you complement A with its complement, you will get always a 0. So again, you can save these identities. Let's box all of them. Okay, so we'll save this. So these are some of the fundamental laws, okay, in Boolean algebra, and we will also review some fundamental identities, also like the laws of commutation. Let's review the law of commutation for Boolean operations. So So if you have A or B, A or B, the logic is the same as B or A. Okay. So this is the commutativity of the OR operator. If you take A and B, uh, you can also check it's the same as B and A. See, what we have been doing here is we have been creating a truth table. And if you do the truth, if you prepare the truth tables for these operations also, you will get the same thing. So these are two, um, this is the validity of the principle of commutativity for the OR operation and the AND operation. Similarly, we have the laws of associativity, just like we have in algebra. So associativity. So here, if you have A or B or C, here you are associating B or C as one operation first and then doing it like this. You can also treat it the same as A or B or C. Okay. And also A and B and C. This also can be done as A and B and C. So this is associating uh, variables using the AND operator. So principle of associativity, law of associativity. You also have the distributivity, the law of distributivity. So here you have, let's say, A and B or C. So we can write it as A and B or A and C. So we have two distinct products here. A and B, or we can also um, consider A or B and C. This is also going to be distributive. So A or B and A or C. Okay. So you have the distributivity, law of distributivity. You have certain other very interesting identities also. Let us just review them. Save this. Yes. So here, let's review. You have certain identities, that is A or A and B, A and B, and this is equal to A. How are you going to prove this? You'll have to proof for this can be done formally. I'll just illustrate to you one proof and perhaps you can. So we start with, for the proof, we can start with, whenever you write a proof, you should be very systematic. It's not just as you do, in your rough work. So here, these are statements. So you can start with the left hand side. That is A or A and B. A and B. Okay. And this is equal to, you can write A as A and 1. You may recall that A and 1 is A. We have already done it some time back, just in the previous slide. And or A and B. Okay. So we have now we can make now, so here you have to give a reason for this and say that A equal to A and 1, since A is equal to A and 1. And this is equal to, you can apply the law of distributivity. So A and 1 or B. We just seen that A and 1 or A and B. This is distributed. And here you know that 1 or B is equal to 1 itself. So this is equal to A and 1. This is because 1 or B is equal to 1 itself. And so this is equal to A, which is equal to the right hand side. So this is how you formally prove. I expect you to be very meticulous while you are doing proofs, proper punctuations, etc. So we have one identity over here. Let's take another identity. So this was the first one. Okay. Let's write this as some Boolean identities. So let's take the second one. Let's take another identity, that is A and A or B. A and A or B. Okay. So this is equal to A. And I'm sure that now you know how to do this. Okay. So proceed exactly the same way. Write a formal proof. Okay. So this is a Boolean identity. The assignment for you is that you have to prove this. Okay, this is very simple, and I'm sure all of you can do it. We have another identity, that is A or not A and B. Not A A and B, and this is equal to A or B. Okay, so this is another identity I would expect you to prove. So these are very small problems. I'm sure all of you can do it. So just do this. Okay. So these are for your assignment, and label it formally as an assignment. Okay. Um, you can also prove uh, not A or B, A or B, and A or not B. This is equal to A. Right out. This is also very simple. If you can see what is actually there. It's very simple. Um, Fifth one is A or B, and A or C. This is equal to A or B and C. Okay, you have to prove this. Sixth one is A or B or A and not B. This is equal to A or B. Seventh is A and B or B and C or not B and C. And this is equal to A and B or C. And finally, A and B or A and C or not B and C is equal to A and B or not B and C. Now, you may see on the left hand side for this eighth assignment, you may see that the left hand side you have three terms, right hand side you have two terms. Left hand side, the first and the last are the same as the first and the last on the right hand side. But you have to prove it. Okay. So we will continue with the laws of Boolean algebra. We have certain other very interesting uh, things which we'll have to review. We have the De Morgan's rule. We have the duality theorem, and then we will begin how to formulate our problems using Boolean logic and how to do simplification. So this is I think, sufficient for today. I would like to thank all of you for attending this class. If you have any doubt, you can certainly ask me at this point.
Hello.
Yes.
So last class you gave us an assignment for 5 minus 9 for 8-bit operators. So,
Yes.
but I wanted to know, can we perform 5 minus 9 for 4 bits?
Yes, you can. That's what
So,
you
so
can
but
try to prove it.
but when we did the sign representation, we have the negative numbers till 8 minus 8 only. So that was
Yes.
confusing. If you could clear
You
it.
can check for yourself. You can check, try to do it by yourself for 4 bits. Follow exactly the same algorithm. Okay? And do it for
Okay,
4-bit
sir.
representation. 4 minus 9. Okay? Of course, you
So
don't
then
have a
why do we?
minus 9 in a 4-bit representation, but try it out. Just try to determine the 2's complement of 9 and add it to 4. Okay?
Okay, sir.